Hello, we are starting chapter 2, and today we are going to talk about water. So, water is a very interesting substance. You guys have learned a little about it in STEM, but we're going to go to a much deeper level of understanding in today's lesson. Mysterious properties of water can be explained by hydrogen bonds. Water has a lot of really interesting properties. Why does ice float when most other solids sink? Why is it that coastal cities tend to be a little bit more temperate than inland ones? How do fancy athletic shirts help remove sweat so quickly? We can talk about these questions in terms of hydrogen bonds. Okay, so first, let's talk about covalent bonds. When atoms in a molecule are held together by covalent bonds, they share electrons with each other. So each shared pair of electrons forms a single covalent bond. This should be familiar to you guys from STEM. In a water molecule, two hydrogen atoms each share a pair of electrons with an oxygen atom, forming a molecule with the formula H2O. Electrons in covalent bonds aren't always shared equally. So in water, oxygen is more electronegative than hydrogen. So basically, it hogs all of the electrons. And really what that means is that the electrons, because oxygen is so massive and is more electronegative, and thus more electronegative, electrons tend to spend more time around oxygen. That is, it is most likely to, at any single moment, find one of those electrons around an oxygen than a hydrogen. And so what that means is that oxygen has a slightly more negative charge. This unequal distribution of charge is called a dipole. So here, electrons are pulled towards the oxygen, or more attracted to the oxygen, creating a slightly negatively charged region. The overall unequal charge is represented by the Greek delta for dipole. And near the hydrogens, electrons are pulled away towards the oxygen, creating a slightly positive charged region. And the reason why you see a delta along with the charge symbol, so a negative or a positive, is because these aren't ions, right? So if you remember from STEM, ions are charged particles. They are particles that are missing an electron, or they have more electrons. This is not that case. Each of them is fulfilling their valence electron. So oxygen is getting access to 8 valence electrons and hydrogen is getting access to 2. It's just that electrons are more likely to be around the oxygen. So because of that, it is a partial charge. So hydrogen bonds. We've learned that hydrogen bonds can form between atoms with a partial charge. So if I have an atom here with a partial positive charge, and I have an atom over here with a partial negative charge, you can form a hydrogen bond between these two atoms. So in water, the negatively charged oxygen of one molecule is attracted to the positively charged hydrogen of another water molecule. And really, it's just the attraction between those two that is called a hydrogen bond. Since water is a molecule with partially charged atoms, water can form many, many hydrogen bonds between its molecules. And this is the property that gives water so many of its unique attributes that helps make life itself possible. So, talking about dipoles again. Dipoles occur in many different molecules, particularly whenever there is a hydroxide, a CO or NH group present. So hydrogen bonds can form between these groups because the oppositely charged regions are attracted to each other. So if you look at that picture, there are positive and negative charges, and those positive and negative charges are attracted to each other in a substance, most likely liquid, which can create hydrogen bonds. Molecules with dipoles are said to be polar molecules. Polar molecules are attracted to water. They are hydrophilic, meaning they love water, and they are water soluble. So water soluble means that water can break apart bonds in other substances. Okay, and the reason why is because if those molecules have some partial charge, so does water. And so water is capable of breaking those charges up because all of those charges are attracted to water. They want to form hydrogen bonds with water. Molecules without dipoles are said to be nonpolar. They are not attracted to water because they do not have a charge. They don't have any partial charge, so they don't care that water has a charge. And because of that, they're hydrophobic, means they hate water or have a water phobia. And they're soluble only in nonpolar solvents, which is why, so if you think of a substance that is nonpolar, a lot of lipids are nonpolar, okay? They're stable molecules. They do not have partial charges or full charges. And so when they are introduced into water, water is not breaking them apart. The charges in the hydrogen bonds aren't attracting the charges in the nonpolar substance because there aren't any. Okay, so that's why they are non-soluble. Oh, that's okay. Okay, so water is arguably the most important biochemical on planet Earth. So without water, there is no. Earth is 75% water. The mass of a cell is 70 to 90% water, and all organisms. So as one example, humans are about 60% water. Without hydrogen bonds, water would exist as a gas at room temperature, which isn't that fascinating. So it's really just the tendency of these polar molecules, right, with dipoles, to be attracted to each other that allows them to be liquid at room temperature. And liquid is a perfect medium for molecules and ions to mix. And so that medium is what life evolved in. Hydrogen bonding in water makes molecules more difficult to separate, and it affects the physical properties of water. So an example of that, you need energy to break hydrogen bonds to make it more difficult to convert water from liquid to a gas than to convert other compounds which lack hydrogen bonds. So a compound that doesn't have a hydrogen bond needs less energy, okay? So that's why water is a good solvent, okay? So a solute is a substance that is being dissolved, and a solvent is a substance that the solute is being dissolved into. Water is an excellent solvent for ions and polar molecules because, again, the charges in water, right, in those water molecules in between hydrogen bonds, are attracted to the charges in ions and polar molecules of other substances. So they'll break all of that stuff up, and the solute will dissolve into the solvent. So when a chemical dissolves in water, the opposite charges collect and separate around the charges in water. Once a chemical is in a solution, it is free to move about and react with all of the other chemicals that are in that solution. Most processes in living organisms take place in solution this way. Okay, hydrophobic reaction. So nonpolar substances do not dissolve in water. When surrounded by water, nonpolar molecules, so like if you're thinking like lipids, or tend to be pushed together by the water. So an example of this is the formation and hydrophobic interactions in a membrane structure. And we're going to learn all about that when we get to cell membranes and transport. But in a cell and cell membrane structure, you have hydrophilic heads, so heads that like water and will bring water in and react with water. And then you have hydrophobic tails inside that don't like water. Okay, and this is a nice sort of, you can think of it as like a two-party system to keep control of what things come in and out of a cell. Okay, transport medium. Water is the transport medium of blood, also of the lymphatic system, the excretory and digestive system of animals, as well as vascular tissues of plants. Because of hydrogen bonding, water has a water has a high specific heat. Okay, it takes a lot of energy to raise the temperature of water. One of the questions I brought up at the beginning of the lesson was why coastal cities are more temperate than inland cities in general. So to answer this question, we have to think about another aspect of water, which is specific heat. It takes a certain amount of energy to change the physical state of matter, right? To go from solid to liquid, liquid to gas, etc. So for instance, here we can talk about ice. We know it takes a certain amount of energy to melt ice and turn it into water. And by the same token, it takes a certain amount of energy, again, that you have to add to the water to be able to boil it, to turn it into steam. Now, this is true about all substances, but what's different, again, about water, we also have to remember that water is linked together by hydrogen bonds. So we need even extra energy into the system to break the hydrogen bonds in addition to the energy needed to change the state of matter. So we talk about the energy that's needed to raise the temperature of 1 gram of a substance, 1 degree Celsius, to specific heat. We then can say that water has a high specific heat. So this is the reason why bodies of water can help cool the surrounding area. So if I have my body of water here and I have a surrounding land, it's going to take extra energy to heat this air over here because energy is also being sucked into this water to heat the water that's close to land. So this area that's close to the land is going to experience a more temperate climate because of this water that's insulating it from the hot air. Whereas somewhere further inland, that insulation isn't happening. But it also, large bodies of water like lakes and oceans are slow to change temperature as atmospheric temperature changes. So due to the high proportion of water in the bodies of living organisms, internal changes in temperature are minimized, making homeostasis easier to maintain. Okay, one of the other questions I posed was how athletic shirts keep you dry, like the quick dry shirts. And to answer this question, let's first take a minute to think about why our bodies sweat. Based on what we've discussed so far about water, how do you think sweating benefits humans? We've talked about how water has a high specific heat, and we've also talked about how that impacts the amount of energy it takes to change water from a liquid to a gas. So if we have a sweat droplet sitting on top of our skin, it's going to take a lot of energy from the surrounding tissue to be able to evaporate that sweat, right? Enough energy for it to change state of matter and also to break the hydrogen bonds. By removing this energy from the tissue, it has cooled you down. This is a reason why our bodies sweat, to cool down when we're exercising. The process of evaporation transfers a correspondingly large amount of thermal energy, and it's one of our most effective cooling methods. Since it takes a lot of energy to freeze water, it also keeps our bodies from freezing. Okay, density and freezing properties. Water is less dense in solid state than liquid, which is why ice floats on water and insulates water below. So the first question that I posed was, why does ice float when most other solids sink? If I have a cup of water and I was to put an ice cube in it, it's going to float. Alternatively, though, if I was to take a tiny grain of salt and stick it into a cup of water, it would immediately sink to the bottom of the cup, even though it's much smaller than the larger ice cube. So why does this happen? Well, what we have to talk about to understand how the ice cube is working is something called density. Density is a measure of the mass of an object per unit volume. This is going to give us a sense of how much mass or how much matter is occupying any given volume. In terms of most solids, the solid is going to have more density than the liquid, in this case water. The thing with the more density is going to sink. It's going to go towards the bottom. The things with less density are going to float or move up relative to the water. What's different about ice is hydrogen bonds. Water can form hydrogen bonds, and in a liquid state, these bonds are constantly forming and breaking in a liquid state. Now, you're going to have to multiple you're going to have multiple hydrogen bonds forming between different molecules. And because they're constantly forming and breaking, that's giving water its fluid nature. As the temperature of the liquid water lowers, it's going to start to form ice. What's going to happen is the water molecules are going to become more ordered because every hydrogen bond that can form is going to form. Because these hydrogen bonds are all forming at the same time, the water molecules are becoming more ordered. They're forming a crystalline structure. Because of this linkage, the water molecules are becoming in a rigid structure, and the rigid structure is holding them further apart than they would be if they were in the liquid state. So because they are being held further apart, they're occupying more volume. And because they're occupying more volume, if we remember our density formula, we said density was equal to mass divided by volume. If I've increased the volume but kept the mass the same, the overall density has decreased because the denominator has increased and the numerator has stayed the same. So because the density is lower, ice is going to float on water. Cohesion. So water molecules have high cohesion. They tend to stick together. Okay, so we talked about why we are sweating and how that's a cooling action for us. Now let's talk about how shirt scientists design shirts to help us out. So this is another phenomenon that we can talk about that you're probably familiar with called capillary action. Capillary action is that thing you see when you have a little bit of water in the bottom of your cup. The water in the straw has somehow risen above the level of the water. It's somehow defying gravity. It might not come as a surprise to you based on what we've already been talking about, but hydrogen bonding is responsible for this action. We talked about hydrogen bonding, linking the molecules together and giving the molecules more strength. The forces that are holding the water molecules together are called cohesion. So water molecules combined with water molecules, but water molecules are polar, so they can also bind to other polar things. The water molecules can also bind to plastic. If I have the plastic of the straw, I can have hydrogen bonds forming between the water molecules and the plastic of the straw. These partial charges are the things that are interacting between the water molecules and the plastic, and this is called adhesion. Okay, so again, cohesion is water with water. Adhesion is water with something else. And this is the thing that allows water to move in long, unbroken columns in vascular tissues in plants. So high cohesion equals high surface tension. This provides surfaces of water with thin film-like covering, allowing water droplets to form and organisms to use as a habitat. So water as a reagent. Water is essential for hydrolysis reactions. So remember, that's breaking down large molecules into smaller molecules. And water takes part as a reagent, which is the substance consumed in a chemical reaction, in some chemical reactions in cells, like photosynthesis.